Okay, in this question we're looking for pretty much a definition of the Doppler effect. So what would be good if you could mention that we're looking for an observed change in the frequency, but you can say the wavelength of the wave. And for the second part of this, to get the second mark, it is emitted by a source that is moving away or towards, or you can bring in relative motion to the observer. The next question is going to ask you what's going on in terms of the observed frequency shift. Now you can't tell exactly from this part of the question because all it says here is it's shifted by a particular amount of hertz. That's not saying if it's moving towards or away from the Earth. Given away in the first part of the question here is that the star is moving towards Earth, in which case that shift will be indicating what we call a blue shift. The wavelength will be getting shorter, the frequency of the waves received will be higher, and that we could say that you can just keep it as the direction is a blue shift, therefore towards the blue end of the spectrum or to a higher frequency. Something of that effect is suitable. Now, knowing that the star is moving towards the Earth with this thing called a blue shift, we need to now determine how fast is the star actually moving towards the Earth. Now do bear in mind we're dealing with a star, therefore it's light, it's a part of the electromagnetic spectrum, and it's not sound. Where do you go for help for this? Well, one thing you can do is go to the 9.5, the Doppler effect here. Will you use this, this or this? Well, if you use this and this, we're talking about Doppler shift in sound. This expression here brings together frequency changes, wavelength changes, and it's got V and of course C. You know this one is about the speed of light, so that's the one you're going to use. Rearranging the one involving delta F, F and V, you can now put the values in that you've been given above. C is the speed of light here, delta F is the amount of shift that is indicated, they've told you the shift, the delta F value here, and divide it by the original frequency that the light would be in the laboratory. You've been given that up here as well for the hydrogen line. Stick all those into the equation, make sure you give the units as well, and you get a pretty big value, 8.5 times 10 to the 3 meters per second. Okay, the question's getting a little more complicated now. Star X happens to have a companion star next to it, and you're then given the distance that these stars are from the Earth, and each of those stars, the light goes through a telescope with this lens eyepiece of that diameter there. So what's going to happen is a diffraction pattern is going to be formed for each of the stars as the light goes through that telescope. I won't define the criterion yet. What we'll do is let's go and see what that would actually look like. So if here's one of the stars in the distance, the light from that star will go through a narrow slit, which in this case is the diameter. That's the diameter of the telescope eyepiece lens itself. And on the person looking, the retina of the person looking at it will then see one of those diffraction patterns, a little bit like that. It's not perfect, but that's the idea. And it's got a great big central maximum, and then you've got it goes to a minimum here, and then another little maximum, something like that. It's not a perfect sketch from me, but you got the idea. Now, what you need to do is think, well, if it's not just one piece of light going through this telescope lens here, it's actually two pieces of light, two different stars. You've got star A, star X and star Y. So this particular one here, because it's not in the same position as this star here, it's going to send its diffraction pattern such that it's going to be displaced where you'll see it. And the Rayleigh criterion, really awfully drawn by me, but the Rayleigh criterion will be achieved when the maximum of one starlight here falls exactly at the first minimum of the other starlight here. And that's what we got as an answer under here somewhere. So the two stars can be just seen as separate images by the eye if the central maximum of the first of one star coincides. So that's the one star central maximum here, and here's the other central maximum of the other star, coincides with the first minimum of the diffraction image of the other star. Okay, the next thing you need to know is what's the actual distance between the two stars, X and Y. So what you've actually got to do here is apply the Rayleigh criterion now about what happens to the starlight for this one and this one when it passes through the eyepiece lens here and eventually falls upon the retina, which I won't draw, but somewhere here. So what does this starlight do? So the angle's exaggerated somewhat, just so you can see what's going on. The main part of this light would go through here and produce, it's very hard to do, but the central maximum would be for that pattern here. Now, since we're dealing with the light in the previous part here, that the eyepiece just resolved the starlight, so just resolved according to here, we know now we are actually dealing with the criterion directly. So that means the light from this star here is going to pass through here, and its central maximum is going to be just where the first minimum of this starlight was here. So there'll be a central maximum here, something like that, very badly drawn, and that, don't worry too much about that. But what you do know is when that occurs, that's a Rayleigh criterion, is just at the limit of the Rayleigh criterion, and that Rayleigh criterion has a known value given to it called theta. You think, well, where do I get that theta value from? Well, I look in the data booklet, and under resolution I see that I've got this here, where theta is 1.22 lambda over b. That is a wavelength. This is the size of the aperture, and 1.22 is because it's a circular aperture and not a standard slit. The 1.22 disappears for a standard slit. You're going to apply that expression there, and if you do, you can actually work out what the value of theta is in the eyeball itself, you know, where it falls on your retina. You can work out that angle there. Now, if you know the angle here, then this is the same angle there as well. That extends all the way to the stars here. There's the distance to the stars from the telescope, and that does mean if the angle's very, very small, which it actually will be because you're dealing with large distances to the stars, then this arc length here that I just sketch in, that arc length there, is pretty much going to be the same as this length here, that chord length there. Well, I can work out that arc length. I know that the arc in this particular case will be equal to theta in radians times the distance between this point and this point here. I've been given that. So what I now need is theta. If I can determine theta, I've got this cracked. Yeah, theta's easy to determine. Here it is. I just put the value of the wavelength in. Just watch out that you get the meters and not nanometers mixed up. B, the value in meters as well here, and I get a tiny angle of 1.17 times 10 to the minus 5 radians. That's that angle here because it's the same as that angle here. I can then just rearrange, it's written in this particular way, the d of the separation, as in the arc length here, is equal to theta times the distance between the telescope and the stars themselves, and that means the separation between the two stars here, d sep, is just equal to 1.2 times 10 to the 13 meters. Very easily done using that small angle approximation there.